So welcome back. If you recall, in my last class, I did your level surface and then normal to a level surface at a particular point, right? So what we are going to do, you will see that we are going to deal with these two a lot. So let me get back to this level surface again. As I have told you that from a function of two variables, the graph of the function of two variables, definitely it represents a surface, right? And again, what happens? This surface itself, you can define in terms of a level surface like this. Is it okay? Right? As somebody told me in my last class that the first one, this is an explicit expression and the second one is an implicit expression. And then I told you that I will tell you something about the normal to this surface because there is some confusion I see among students. Like say, you know that if I want to find out the normal to this surface at the point say x0, y0, say z0. So then what I normal will be simply given by your fx, fy, fz, right? And of course you are going to evaluate it at the point x0, y0, z0. Is it okay? Are you guys here?
Yes, sir.
Yes,
okay.
sir.
Okay, fine. So now, if you look at this function, what happens? I can get a level surface out of that graph of the function. I can do it like either like this, okay? Either like this, or I can do it like this also. F of xy minus z equal to 0 also. I can have something like say, I can have something like this as well, isn't it? So now, then what is going to happen? In this case, a normal to the surface at the point x0, y0, z0, that is going to be given by your for this one, that is going to be given by minus fx minus fy 1, right? And of course you have to evaluate the point x0, y0. And for this one, that is going to be given by simply fx, fy minus 1. Fine? Have you able to appreciate the difference between these two? Like, is it okay with everybody? I have simply computed it from the formula of gradient of that function of 3 variables. Is it okay? Up to this, it is fine.
Yes, sir.
Right? So now you may be thinking, which one should I go for? Whether I should go for this one or this one. Okay. See, what is happening here? I have something like xyj, and basically I have a surface. Right? So suppose this is some kind of surface, and suppose I am taking this point x0, y0, z0. So now, can you tell me the difference between these two?
One vector is inside and one vector is outside.
How do you know which one is inside? The surface may be, it may not be a closed surface. Then how are you going to define outside and inside? maybe, I mean, you are getting it, but you haven't been able to explain it clearly. See, you have to look at the last component of the vector, both the vectors. So if you look at the first one, the last component, it is positive, that j component, and here it is negative. So what you should know is that in this case, you are going to get something like this, something like this. It is going to be upward in the z direction. Whereas in this case, you are going to get something like this. That will be the difference. As somebody told me, it's inside and outside. Yes, it will be something like that. See, if you suppose it is a sphere, right? So again, like even on the surface, if I take it like this, there can be another normal at this point, right? So they are still outside, right? They are still outside. But you can see that in this case, this is in the downward direction, right? So it is about the upward and downward direction. So basically, like say, just by looking at the last component, you'll be able to know whether it is going to be, I mean, upward or downward. That's it. You don't need to worry about it. Okay. So accordingly, you are going to adjust your number. That's it. Is it okay? Is it okay with everybody?
Yes, sir.
Yes, sir.
Right?
Yes, sir.
So now let me come to implicit function theorem. So you may have done it earlier. So I'm going to do it for a function of, I mean, 3 variables, and I mean, you can easily extend it to function of n variables. And I am considering a function of 3 variables because I'm going to deal with level surface of a function. That's why. Okay. So implicit function theorem. Implicit function theorem. So I will show you the formal statement in this slide. I'll run these slides for some time. Okay. So what it tells you that suppose you consider a function of 3 variables, say f of x, y, z. Okay. And then I am also assuming that this partial derivative of capital F with respect to this, and they are, I mean, continuous. Say, okay, I am considering the function in some domain omega, which belongs to R3, So it is a subset of R3, and I am assuming that they are continuous in omega, and suppose at a point x0, y0, z0, use this partial derivative with respect to j, it is non-vanishing. Okay? So then j can be expressed as a function of x and y explicitly in the neighborhood of your x0, y0, j0. Okay, so that is the implicit function theorem for a function of 3 variables. Is it okay? Fine. And before that, what happens whenever this happens? Definitely, you will be able to find out the partial derivative of j with respect to x and y. So then this is going to be given by your fx divided by fj, and this is fy divided by fj. Okay, probably you already know this. I'll give you one example. I mean, like why this condition is required. So obviously, I mean, you can see that for the partial derivative with respect to x and y to be defined, obviously this denominator has to be non-zero, right? I'd like to give you one example. I'm not going to prove this theorem because I'm simply going to make use of this theorem later on. Let me just okay. So I'll take one. So this statement is okay, right? It is simply a statement. Okay, fine. Let me take one example. So what you have to do, if possible, you have to solve this equation z square minus x square minus y square equal to 0 for j in terms of x and y, say near the point, say 1 1 square root 2, 1 1 minus square root 2, and 0 0 0. Okay, fine. So now can you tell me what the expression is going to be nearby these 2 points?
Exist.
Z equal to square root x square plus y square. For this, it is going to be z equal to minus square root x square plus y square. Because see, this point itself, it gives you an idea. Because you know that in order for the third component to be negative, you must have this formula. So now, what about this formula? What about that point? What implicit function theorem? What did it tell you? That
Not
partial
applicable, sir.
derivative with respect to j in that particular point, it has to be non-vanishing, right? Is it okay? Right? Partial derivative has to be non-vanishing. Okay. So at this point, it is not possible. At this point, it is not possible. Anyway, I mean, in that given function, of course, this has been given. This has been given. I think just a minute. Just a minute. Okay. Okay. Fine. Just a minute. I think I should rope in that equation. I still haven't roped in the equation. Just a minute. Just a minute. See, implicit function theorem. I told you that. Just a minute. I told you about the function, but what I should have told you, just a minute. So this can be solved. Okay. This function of 3 variables equated to a constant. So that is nothing but this represents the level surface, right? This can be solved for j in terms of x and y if in terms of x and y in the neighborhood of this point, right? If partial derivative of this function with respect to j is non-vanishing at this point. Is it okay? Are you getting my point? What I missed earlier?
Yes, sir.
Yes.
Right? You have to have an equation, right? Otherwise, how are you going to get, I mean, j in terms of x and y? Okay. Okay. So now, obviously, here, this is my f of x, y, j, and 0 is nothing but it is the constant c. Okay. So now, can you relate this point to implicit function theorem? Obviously, like if you take I mean fz that is simply your equal to 2z, and this is 0 at 0 0 0. So you cannot express I mean z in terms of x and y in the neighborhood of 0 0 0 origin. And does it tell you something else also? I mean, I mean, the things are going to unfold little by little, and for example, okay. Okay, so this is simply right. Okay, for example, I mean, now can you see what is happening here? Can you see what is happening here? Of course, I mean, I could have taken either this part and I could have taken this part also. Okay, I could have taken that part also. So now, can you see what is happening there? Can you see what is happening there at the origin?
If you take any neighborhood of origin, then that cannot be that is not a graph of some function, because if you consider some neighborhood of origin, then in that neighborhood the point has two possibilities. It is either its image has two possibilities. It can be either some points in upper half plane or some points in lower half plane, because there is cone downward also.
Upper and lower. Can you repeat it? Upper what?
Upper man means z greater than 0.
Okay.
And lower means I mean z less than 0, because if you consider some neighborhood of origin, then the image of some image has two possibilities. That means z can take positive or negative value.
No, positive or negative value in terms of what you cannot get. You are trying to get into something.
Yeah, I mean we can we can write z equal to some gxy in the neighborhood of 0, 0, 0, because the issue is if you consider neighborhood of 0, 0, 0, we can see the cone on downward direction. So
okay.
Has two possibilities.
Okay, I'll stop you there. Can you think some in terms of some tangent plane or something like that, or a normal?
Yeah, I think.
See what happens. The over there, the normal is going to be vanishing. Okay, the normal is going to be vanishing, right? You cannot get a normal over there. You get no direction for the normal. Okay, right? I'll come back to that later on. Okay, now just one thing. Let me change this point. Let me change this point. So obviously, say suppose I take the point 110, right? 110. This still tells me the implicit function theorem that you cannot get z in terms of x and y. Fine? Okay, at this point, in the neighborhood of this point. Is it okay?
Yes, sir.
Right? But what about, I mean, x or y in terms of yz or zx, z and x? Can we do that at this point? Say, this was about expressing z in terms of x and y, right? Z in terms of x and y from this expression. Now, if I change this problem to expressing, say, x in terms of y and z, am I going to get that here? From here, can I do that in the neighborhood of this point?
Sir, actually, yes, sir. This point is not in our level surface, because if you plug in this point in z square minus x square minus y square, we are not getting 0.
Okay. Yes. yes. Okay. Yeah. Fine. That is I'm happy with that answer. But suppose I had something like a point x naught y naught z naught. What happens? Like say suppose at this point this equation is satisfied. Then suppose your fz at this equal to 0, but fx at this point is not equal to 0. So then, can I express x in terms of y and z in the neighborhood of this point? Yes or no? From implicit
So I think
function theorem?
because implicit function theorem tells this one, because we can do it.
Yeah, we can definitely do it because it depends upon the partial derivative of this. If this is non-vanishing, so definitely for the variable x, you should be able to express x in terms of y and z for this expression. I mean, of course, I mean this at x naught, y naught, z naught, that level surface. I mean, x naught, y naught, z naught has to be a point on the level surface. Okay, fine. See, I'll come back to this again. I'm going to discuss some more concepts, and then it will be clear to you why we are emphasizing so much on implicit function theorem. Now, I have already done this. Curves and their tangents. Just one thing I'd like to mention here. See, when I was describing a space curve. So what I did, that you take any point P, X, Y, J there, and then I mean what we did, we defined a vector R. So R was simply some. Okay, fine. And and then we define T in some interval. Okay, so here I define this curve to be created from the trajectory of a point moving in the XYZ space. Okay, now it is not necessarily, I mean, the curve can be traced out by a trajectory. It is not like that. Like say here, they actually represented x, y, and z. They represented d coordinates of a point at time t. Okay, but I can take any arbitrary, continuously differentiable functions f12, f2t, and f3t, isn't it? They may not represent the coordinates of a point. Even then, I can get a space curve out of this. Is it okay? See, I mean, designating the first, second, and third component as the position of particle, it is easier for us to visualize, right? Even if they are not the position of a particle, even they are not exactly the position of a particle, still we can get a curve out of that. So, and again, another thing that day I missed, that when I define the tangent to the curve at a point, so then I simply showed you the derivative from the definition. But you should also remember that it is very easy to work out. So eventually, the derivative can be written in this form. Okay, I'll come back to this once again. This is just to tell you that they don't necessarily have to be the position of the particles. Okay, so now the concept. Okay. So this you may call it theorem, exercise, both. Okay. Before that, let me ask you. So suppose I am considering two level surfaces given by can you tell me what will be their intersection of two surfaces? Yes. What will be the intersection of two surfaces in space?
Curve.
It is going to be a curve. It is going to be a curve. It is going to be a curve. Okay, fine. So now the next theorem or exercise, it is going to be on this fact. It is going to be on this fact. Okay. So let your x0, y0, z0 be a point on the curve C, on the curve C, simply described by the equations these two. Described by the equations f1 xyz equal to c1 and f2 xyz equal to c2. So then the vector grade f1 cross grade f2 at the point x0 y0 z0 x0 y0 z0 is a tangent, to the curve C at your x0 y0 z0. Have you come across this before? Have you come across this before? I think no. Okay. So, see, let us have a look back at this statement. So here, firstly, we are talking about two level surfaces given by these two equations. And then we are talking about their intersection, which is nothing but a curve C, Okay. So then, what we have done, we have simply taken a point x0, y0, z0 on that curve. Okay. And then we are claiming that a tangent vector to the curve at this point is given simply by this expression. That's it. Okay. So let us try to prove it. Again, I am going to summarize all this. You don't need to worry about it. I'll do a quick summary of what I have done. Okay. Okay. Suppose this is the surface. Here say U1 equal to C1. Will I take U1 or F1? Okay, F1. F1 equal to C1. So basically F1 of x, y, z. Okay. So then now what I'll do. So then I'm taking another. Maybe. Which way it will look better? Okay, I can take another surface. Say this is F2 equal to C2. Say F2 equal to C2. So far so good, right? And this is their curve of intersection C. Okay, this one is C. Okay, so suppose I am taking this to be the point x0, y0, z0. So now, what is going to happen? For this surface, a normal at this point is going to look something like this. Okay, so this I can call as grade f1. Is it okay with everybody? Fine. Okay.
Yes, sir.
And for this surface, your normal may look something like this. Say this is your grade of f2. Okay, fine. So obviously, then what is going to happen? Now, if I take the cross product of these two normals, at the point x0, y0, z0. So this new vector, let me call it say t bar. No, this new vector, it is going to be perpendicular to. It is going to be perpendicular to what? Both grade f1 and grade f2, isn't it? Right? At that particular point.
Yes, sir.
Is it okay?
Yes.
Right? So basically, they are going to form a triad. Delta, grade f1, grade f2, and this t. Right? So then, at this point, if you have another vector which is perpendicular to grade f1 as well as grade f2, then what must happen? That must be what? That must be
Tangent to C.
tangent to
Tangent to
the
the
curve C at the point x0, y0, z0. This is as easy as that. Okay, that's it. This is the proof. Okay, fine. So now, let us take an example. Okay, fine. So let us take again, I'll come back to this. Okay, fine. See here, another thing I need to tell you. First of all, this grade f1 cross grade f2 at x0, y0, z0. The very first thing that I should have told you that has to be non-vanishing. Remember, that has to be non-vanishing. So basically, only when this is not equal to the zero vector, only then I'll be able to define a tangent at that point. Remember that. Is it okay? Fine.
Yes.
Is it okay? Right? So that has to be your first condition. Okay, the non-vanishing part I'll come back again later on. Okay, so now in Simon's book, they have taken the same problem. So this is about finding a tangent to the curve of intersection of these two. Surfaces. Okay, so how we are going to do that? And in Simon's book, what he has done, he has fixed this C1 and C2 at the beginning. He has taken C1 to be equal to 0 and C2 to be equal to 1. And then he explained, and then he again came back to these two equations by taking C1 and C2 arbitrarily. Okay, so what I'm going to do, I'm going to combine both of them. I'm going to take C1 and C2 arbitrarily. Okay, now the very first thing that you have to consider. So let me find grade f1 cross grade f2. Okay, how is it going to look like from these two? Okay, so of course this one is f1 xyz and this two is f2 xyz. Let me write equivalent. Okay. No, fine. This is fine. Okay. So now, this is 2x, 2y minus 1, and this is simply 0, 0, 1. Is it okay? Fine. So this is going to give you 2y minus 2x 0, right? Yeah. Okay. Fine. So now I'll ask you one question. Now see, I want these to be non-zero, right? I want this to be non-zero. Is it okay? In order to define a tangent. Is it okay with everybody?
Yes, sir.
Right?
Yes.
So then, if I am to consider my domain of definition, of those two functions, domain of definition of those two functions, I mean, what should that be? See, let me tell you that what is going to give this vector as 0?
Origin.
Is it only origin?
X axis,
No, Z
X
Z
axis
also
and Y
be
axis.
non-zero.
So basically, if x,
Z axis.
yes, z axis, right? Over z axis, x and y are 0, isn't it? X and y are 0 over z axis, right? Isn't it? Okay, so that
Yes,
means
sir.
if I choose my domain, in such a way that my domain does not include the z axis, then any curve of intersection, I mean coming out of two surfaces in that domain, is always going to have in all the points you'll be able to define a tangent. Is it okay?
Yes.
Is it clear to you now? Okay, so that is
Yes,
why we are going to choose this to be your R3 minus Z axis. R3 minus Z axis. That is what we are going to do. Okay, so now let us try to see, I mean, how it will look like. Okay, let us see how the surfaces are going to look like. Okay, so this is X, this is Y, and since I'm going to avoid Z axis, let me do something like this. So now, if I simply take this, so then what is going to happen? Z plus C1 is going to be X squared plus Y squared. Okay, so if say hypothetically, if say C1 greater than 0, so then if I take this point to be say minus C1, so then this is going to represent the parabola x squared plus y squared minus z equal to C1, isn't it? Fine. Is it okay with everybody?
Yes, sir.
Right?
Yeah.
Because if you plug that in there, for example, suppose you take xy to be equal to 0, so then your z equal to minus C1 is definitely going to satisfy that. Although, I mean, like say we are avoiding that, just to check. So now, suppose your C2 is also greater than 0, only for the sake of drawing this. Okay. This may not be, I mean, greater than 0. It may be less than 0. Also. But in order to draw the figure, I'm assuming that. Okay. So then somewhere here, say suppose, I mean, C2 is here somewhere, right? So then this is nothing but z equal to C2. So that is going to be some plan z equal to C2. And what it is going to do, it is going to cut this paraboloid. Is it a paraboloid? Yeah, it is a paraboloid. Yeah, it is going to cut the paraboloid where in the circle simply x squared plus y squared equal to C2, right? Okay, so this is my curve of intersection. Is it okay? Fine.
Yes, sir.
Yes.
Okay. Now,
Sir,
just some
hello.
interesting facts will come out here. Interesting
Hello,
facts. Yeah.
This circle will be x square plus y square is equal to c1 plus c2 or only c2?
C1 plus C2. Yes, you are right. Yes, you are right. Okay, I have got another clue. So C1 and C2 is going to decide now something. Thank you. Somebody has pointed this out. Is everybody getting it? Because if I plug in here C2, this is going to give you x square plus y square equal to C1 plus C2, right? So that gives me one condition. I told you that, I mean, although here, for the sake of visualization, I have taken, I mean, C1 and C2 to be greater than 0. What I need, I simply need C1 plus C2 to be greater than 0. Okay, so by choosing this, you can choose C1 and C2 individually. Are you getting my point now?
Yes, sir.
Right? So your C1 can be negative, but it should be in such a way that C1 plus C2 is strictly greater than 0. Is it okay? Fine? Okay. So I think I'm done here, but just a minute. I'd like to bring your attention to another fact. Okay. Fine. Okay. So now, if you want to have a parametric representation, of the carbon intersection, parametric representation of the carbon intersection, can you give me that? Yes?
X is equal to root under c1 c2 cos theta and y is equal to root under c1 c2 sin theta.
Okay, that is an easy way of doing that. Can you do it without sin theta and cos theta?
X is equal to t and y is equal to root under c1 plus c2 into minus root t square.
Yes. Y equal to, I will tell you, minus t squared, right? Z.
Z
equal
is
to?
c2.
Why? Z is? Z cannot be anything other than that one. Okay. Z cannot be anything other than that one. Okay. Fine. So far so good. Now, okay. Now give me the range of t. Yes, you have a clue here. Give me the range of t. You have a clue here.
Minus root over c1 of c2 to plus root over c1 plus 2.
Should I mean, in order to avoid confusion, should I do this? Yeah. Okay. Fine. Now, is it clear? Is it clear to everybody? Is it?
Yes.
Yes. Okay. Now there is something still more to that. Something still more to that. I want to come to. Just give me a second. Okay. Did I miss something? Okay. I want to treat this problem completely. Okay, fine. So now let me come back to the tangents. Let me come back to the tangent. If you recall, the tangent, it was giving something like 2y, 2x, 0, right? 2y, 2x, 0. Okay. So basically, the tangent vectors, the z component of those vectors are going to be 0. That's it. Okay. But they will be such that, say, suppose now I'm considering this circle. This circle is nothing but x squared plus y squared. This is equal to c1 plus c2. Say. This circle is x squared plus y squared plus c1 plus c2. So now, suppose I have taken this particular point. Say I have taken this particular point. Obviously, you can see that here. Here you can, at this particular point, you can see that the y coordinate. I mean, that is your less than 0, and x coordinate is greater than 0, right? So I'll just show you a demo of how the tangent vector is going to look like. So firstly, this length is y. So what I'm going to do, I'm going to 2 units of this. So it is going to look, say, maybe something like, yeah. Just a minute. I have to start at this point. So 2y, 2 units. Yeah. No, just a minute. Was it 2y? Just a minute. Was it 2y or minus 2y? Sorry. I'm fine. So, okay. See, then what I'm going to do, say, suppose this is my point, say, x0, y0, right? So that means this is your x0, this is your y0, right? And from here you can see that this y0 is less than 0. Is it okay? Fine. So at this point, I am going to move 2y unit. Okay, since y0 is negative, so I'll move something like this toward this. Say, suppose this length is say 2y0, right? And then I am going to move 2x0 along y-axis, and see here x0 is positive, but minus 2x0 is going to be negative. So I have to move downwards. So what is going to happen? It is going to be something like this. Now, if you join this vector, so then you will see that this is going to be something like this. Is it okay with everybody? Right? Is it okay with everybody? Okay?
Yes, sir.
Yes.
So basically, what is going to happen if you want to draw the tangent vectors here? So here, see, it is going to be something like this. It is going to be something like this. Okay. So, yeah. So it is going to be something like this. It is going to be something like this. So now, have you now understood why these vectors y minus x, see in 2D plan, y minus x or minus yx, it is always going to represent some kind of rotation. Is it clear now? See, if you exactly take this, your orientation is going to be this. If you take it like minus yx, your orientation will be in the opposite direction. But still, you are going to get some kind of a rotational movement. Is it clear now? Whenever you consider a rotation, you can always have this as representing some kind of rotation. Is it clear? Okay, fine. So now I would like to do one more exercise here, page 16, 3.3. I'll just give you a hint how to work this out. Then I move to my next section. Okay, so the exercise is your f is a real valued function. F is a real valued function in some domain omega belonging to R3, and of course I am assuming that f is C1 in omega. Okay, and of course I have been giving that grade of f is not equal to 0 vector. Okay, and this is the level surface, say I am calling it SC. SC. This is the level surface SC. Okay, and again you have another curve C. This is curve C. It is given by your this vectorial notation, your f1t, f2t, and f3t, and of course t belongs to some interval I in the real line. So now, if you suppose that this curve C lies on the surface SC, right? So then obviously what is going to happen? This point is going to satisfy this equation, right? See, it's situation is something like this. My situation is something like this. See, this is your f x y z equal to c. So this is the surface with SC. Okay. So now I am considering. Say, suppose this is the curve. Oh, this is some curve C. This is some curve C lying here. Is it okay? Fine. So then this vector R, right? So this R can be defined by f1t, f2t, f3t. Okay? This is something like this. Is it okay? So this is what they are saying. Is it fine? Right? So that is why. So that means x, y, z coordinate for a point lying on the curve, it is given by f1t, f2t, f3t, right? So that is why for this curve lying on the surface, this equation, I can write it as is it okay?
Yes, sir.
Right? So now you have to show that at each point of C, the vector tangent to C is orthogonal to the vector normal to SC. Okay, you have to show that you take any point here, you draw a tangent. You have to show that this tangent is orthogonal to the normal that you are going to draw to this curve at this particular point. That's it. Okay, and you will see that it's very straightforward. Okay, see, if I take this equation is definitely satisfied on the curve C. over the surface SC. Is it okay? Fine? Isn't it? So that is why your df dt, this is going to be equal to 0. Is it okay? But if I use chain rule, this is going to be del f del. This is equal to 0, right? So this I can simply write as your what? fx, fy, fz dot your dx dt, dy dt, dz dt. This is equal to 0. Is it okay to everybody? Right?
Yes.
Yes, sir.
Right? But what is this? This is nothing but grade f, isn't it? And this is nothing but, if you define that vector, joining a point on the surface, joining a point on the curve C as this R bar, so it is nothing but this, isn't it? Or what you can do, just a minute, I have written dx dt, right? So you can simply write it as f1, f2, f3. Then it will be more, f1, f2, f3, right? So this is nothing but R prime t. And that's, you take any point, x0, y0, z0 on the curve, and then, proof is complete, isn't it? Is it okay? Fine. This is nothing but, and if you simply take the point x0, y0, z0, so this is nothing but what? The tangent to the curve C at the point x0, y0, z0, and this is nothing but what? A normal to the surface SC at the point x0, y0. Okay? Clear?
Yes, sir.
Yes.
No, you guys are silent today. I don't know why. Can you just give me 1 sec? I'm just getting a call. Okay, fine. So now, this partial differential equation book, that Introduction to Partial Differential Equation book by Tho and Zach Maglaro, you please do exercise 3.6. This is pretty straightforward. 3.6 on page 16. Page 16. Okay. Okay. So now I'll just I'd just like to mention one thing. You already know it's safe. Earlier in our ODE class, what we did, we considered a first order ODE of this form. ODE of this form. Your say with some initial condition, say x t not equal to say x naught. Okay. We have already seen that. This integral equation e naught to t, you say f. Then what should I write? Maybe let me follow. Simon's rule. I can something like this. Something like this. Is it okay? If I want to solve this equation, right? I can solve it like this. Isn't it?
Yes, sir.
C, I am going to find
Yes,
from the
yes.
initial answer, right? So I just want to give you a picture of how you are going to visualize it. Only for that I'm writing this. See, this is T. Suppose this is XT, and somewhere here you are going to have say this is T naught. This is T naught. So then your solutions, I mean, they may look like this. So what we are going to do, basically, if you draw a vertical line here, so you are going to have different initial conditions over this point. Is it okay with everybody? The initial conditions will be given by this, because, right, for a particular curve, suppose this is the initial condition. So this is simply going to be what? T naught x T naught, isn't it? T naught x T naught, and that is going to give you the initial condition here. And so this is going to be the solution curve passing through that point. Okay, and you know that this is nothing but a one parameter family of curve. We have always seen this earlier, right? If you have the first order differential equation, so then the solution we are going to get as one parameter family of curve. Is it okay? Fine. Okay. I'm doing this because I'm going to use this a lot in the near future. Okay. Now, let me come to yes, integral curves and surfaces of vector field. Okay, integral curves and surfaces of vector field. Okay. Now, see, integral curve we have already seen, right? Do you remember integral curves? The solution curves. The solution curves coming out of a given differential equation, they formed integral curves, isn't it? Earlier also I did that. Okay. Now what is happening? Surface I will come later on. Now you can see that another term is being involved here. So what is that term? That term is that they belong to some vector field. Okay. So what is the difference between like say whatever integral curve that you have learned so far, and again grouping in a vector field here. So what is that? Say suppose I am considering a vector field V, say, vector field V. Of course, this vector field V, again I am considering 3D space. It is going to have 3 component PQR, and as before, I am defining the vector field on some domain omega belonging to R3. So basically, that means your V as a vector, it is a function of x, y, z, and so as P, Q, and R, right? So then I will define a curve. C. I'll define a curve C as the integral curve of this vector field. If at each point, say suppose this is C, each point C on the curve, your V is a tangent. Is it okay with everybody? Right? How this vector field V is related to this curve C? If we are to define a curve, say space curve, as the integral curve of the vector field V, then at each point on the curve, at each point, say suppose I have taken an arbitrary point x0, y0, z0. So then what must happen? This vector V at x0, y0, z0, it must be a tangent to the curve at that particular point. Is it clear now? Is it okay with everybody? Yes? The definition of an integral curve of a vector field. Yes?
Yes.
Yes? Don't get afraid by I mean just looking at this term vector field. Don't get afraid. Fine? Okay. So just a minute. Now, see, the thing is that you cannot define something very arbitrarily. Okay, so they have to come under some assumptions. Okay, now when I define an integral curve of a vector field, when I define that vector field, the very first two conditions that I have to impose is, firstly, your V has to be non-racing. This is the first condition. Okay, fine. And the second condition is these individual components PQR, they must be what? Continuously differentiable. Where? In omega. Okay, so continuously differentiable means the first order derivatives with respect to x, y, z, right, must be continuous in the domain omega. So under these conditions, if again V being a tangent vector at each point C is satisfied, then I say that C is an integral curve of the vector field V. Is it clear now? Is it okay? Fine?
Yes, sir.
Fine. So for example, if I consider say the vector field say V, earlier we have seen y minus x0, right? So then for this to be related to an integral curve, what we must have? The vector field must be defined. The vector field must be defined in some domain which doesn't include the what? Z-axis, isn't it? Which doesn't include the Z-axis. Is it okay? Fine?
Yes, sir.
Yes,
Isn't
sir.
it? Why that is so? Why that is so? Because the prerequisites for defining an integral curve is that firstly, the vector has to be non-vanishing. Is it okay? Fine. What about this? Can you give me a domain for? Again, I have taken all these examples from. Say, suppose I have this vector field. Can you tell me where I can define them? Yes? Can you tell me where I can define them? If I have to define an integral curve for this vector field, where should be my domain? Yes?
R3 minus ZX.
So whole R3.
R3 minus
Z axis.
No? What?
So the third
Where is your
component is
concern? Just
non-zero.
tell.
Third component is non-zero for any xyz.
So because second component is x plus y by z.
Your concern is the second component, right? Everybody's concerned is the second component because I know that the third component is anyway. Third component, can it give you 0? Third component, can it give you 0?
No.
No. So, and again, what about the second component? Only thing is that the second component cannot be defined for z equal to 0, right? Isn't it? Second component, it cannot be defined for z equal to 0. I don't have any problem with non-vanishing part. Is it okay with everybody?
Yes, sir.
Right? Whatever happens, because of the third component, it is always going to be non-vanishing. But the problem lies on the second component because it is not defined for z equal to 0, right? So then what you have to avoid? You have to avoid the plan z equal to 0, right?
Yes,
Agree or
sir.
disagree?
Yes, sir.
Yes. Now the thing is, should I define the domain omega as simply R3 minus Z plan? Yes?
So it is domain, so it is connected.
So
So either above plane, above.
exactly. Either Z greater than 0 or Z less than 0. See, remember, we are talking about derivatives. We are talking about differential equations, right? Isn't it? I want continuity of the function. I want the continuity of the function. Remember, I mean, in a domain, I don't want the domain to be broken somewhere. You remember in ordinary differential equation also, we did something like that. Is it clear now? Is it okay?
Yes, sir.
Yes, sir.
Right? So that is why the domain is the region above J plane or region below J plane. That's it. Okay. It cannot be a union of both of them. Remember that. Okay. So now I'll simply run you through. Some slides. So I have. Okay. So this is one of the form of implicit function theorem. So here, see, they have defined that function is clear. Containing the point x naught y naught z naught, where f x naught y naught z naught equal to 0. So basically they are considering f x comma y comma z equal to 0 as your level surface. That's it. Okay. So now the remaining portion is the same. Whereas I defined what? Omega as my domain of definition, right? Okay. So these are the exercises you can try at home. And see, as I have told you, this particular problem in Simon's book, he has explained it through this C1 to be equal to 0 and C2 to be equal to 1. Okay, whereas I have already gone for the general case. Okay, and this one also, this one is also like your implicit function theorem. I'll come back to this later on. I mean, if I use this for the time being, let us keep it. So this is what I have done for this as the tangent vector to this curve at this point. Okay, so here you see the demo of this. In fact, I had taken this to be u1 equal to c1, that f1 equal to c1, and this is F2 equal to C2, and accordingly I adjusted the gradients. Okay, fine. And then I told you to do this exercise 3.6, this one. This we have already worked out. Okay, and this is pretty straightforward. Vector tangent to the straight circle, you can easily do that. Simply take gradient of this one and this one, right? And take their cross product, and you evaluate the cross product at this particular point. That's it. Okay, fine. And then this is the definition of integral curves of vector fields. Okay, so these are the two conditions. Firstly, what you do, you assume that V is a vector whose components are P, Q, and R. They are again functions of X, Y, Z. Okay, so this is a vector field in some domain omega in R3, and it satisfies the following two conditions, as I have told you. First, the vector V has to be non-vanishing. Again, see, remember, V has to be non-vanishing doesn't mean that your P, Q, R, they have to be zero simultaneously. No. If one of them is non-zero simultaneously, that is good enough for us. Okay. The second thing is that the first order partial derivatives of P, Q, R with respect to X, Y, Z must be continuous in omega. That's it. And as I have told you, this is the definition. A curve C in omega is an integral curve of the vector field V if V is tangent to C at each of its points. So the integral curves are going to look like this. Okay. Then again, I will again define integral surfaces, and they will be coming out of union of integral curves that I will tell you. Okay, and here they are showing different vector fields from which you can get some integral curves. So this one is a problem that we did earlier. Like, only the difference is that earlier the vector was twice this vector. Okay. Fine. So maybe I will finish your class today here, and what I'm going to do. So tomorrow we are actually going to start with partial differential equations. So tomorrow we are going to deal with some partial differential equations and their solutions. Okay, but all these things that we have learned, they are kind of prerequisite, because later on I am going to relay all of the solutions or the initial conditions of related to those partial differential equations to some geometry. So that is why this was very, very important. Okay, so then I'll see you tomorrow.
Excuse me, sir.
Yeah.
Sir, on 14 we have a test, but 14 is Diwali, so can you postpone it?
Okay, maybe I'll